Okay students, point estimation of process parameters, or we can simply call this topic estimation of parameters. Now you know that a random variable is described by its probability distribution, okay, and the probability distribution is actually described by its parameters. For example, the parameters of normal distribution are mu and sigma square. Mu is mean and sigma square is variance. And parameter of binomial distributions are n and p, where n is the sample size and p is the success rate. And parameter of Poisson distribution is lambda. You can see these parameters in their formulas, or we call them probability density functions or probability distribution models. Okay, so in those formulas you can see, means for example in the formula of normal distribution you will find these parameters mu and sigma square. Means that the probability distribution is described with the help of these two parameters, whereas binomial, the formula of binomial distribution, or we call it probability density function of probability distribution, is described by these two parameters. You can see this in the formula, while the parameter of Poisson distribution is lambda. Means that Poisson distribution formula will contain this parameter, and this probability distribution will be described with the help, means through this through the values of lambda. Okay, now the parameters are actually estimated through sample data and are called, those estimated values are called as estimators or point estimators, right? So in order to estimate parameters, normally parameters are unknown and we have to estimate these values, and estimation is made with the help of the samples or the measurements that we have made on the samples which are collected from a certain probability distribution. Okay, so we call them as estimators. If you can recall, estimator, if you recall that a statistic is a quantity that is the measurement which is made on the sample in order to estimate parameters of a certain population, right? So estimator in a sense is also a statistic because we are making measurement from the sample data. Okay, now there are two properties for a good point estimator. One is that it should be unbiased, means that the expected value of the point estimator should be the parameter being estimated. Means that they both must be same. The sample, for example, sample mean is a good point estimator or unbiased point estimator for population or mean of the probability distribution. Okay, I repeat that sample mean is a good or unbiased point estimator for the mean of the probability distribution, and the variance or the sample variance is an unbiased point estimator for the mean for the variance of a probability distribution. Okay, so the means that the expected value of point estimator should be the parameter being estimated. Mean of sample is an unbiased point estimator for mean of the probability distribution, and variance of the sample is the unbiased point estimator for variance of the probability distribution. Okay, so this is one thing. And the second property of a good point estimator, that it should have minimum variance. So when you collect many different samples and you make a point estimation, or you calculate a value from there, or statistic, you calculate statistics from different samples, and then you calculate their variance, means how much that value is varying. Then you have to find out the minimum one. So the one that has the minimum variance is called it will be considered as a good point estimator. Okay, for example, means this statement means that a minimum variance point estimator should have a variance that is smaller than the variance of any other point estimator of that parameter. Means for a parameter can be estimated through multiple through more than one uh, type of point estimators. Okay, but a good point estimator will be the one that has the minimum variance. Okay, means you are calculating from one sample to another to another to another. Means for example, you have 15 different samples and you are calculating you are making measurements to get a point estimator for a certain parameter. Okay, and out of all those you will choose the one which has minimum variance. Okay, so these are the two properties of a good point estimator. Okay, now sample mean is an unbiased point estimator for population mean. Sample mean is represented with x bar and population mean is represented with mu. It can be expressed like E of x bar is equal to mu. This E is actually the estimation operator, means that the estimated value of mu. Okay, so we estimate this value of mu by the value of x bar or the sample mean, or it can be represented like this. Here the hat symbol, this on the top of mu, is actually an indicator of an estimator, or the estimator for mu or the estimator for population mean is the sample mean, and the sample variance is an unbiased point estimator for population variance. Because you know that the sample variance is represented with s square and population variance is represented with sigma square, right? So this one is the point estimator and this one is the parameter. Okay, and here we can write it like this. So here is the estimator operator again, the estimation operator again, the value of s square or the sample variance is an estimated value for, or the estimator for the population variance, or we can write it like this with a small hat on the top of sigma square. The estimated value of sigma square is actually the sample variance, right? So for example, let us consider a whole lot of the ball bearings produced by a certain manufacturing process. Okay, and we want to find out the mean, like this one, mean, and the variance of the inner diameter of these ball bearings. So out of all these ball bearings, the population of ball bearings, we select a sample of 20 ball bearings, right? So maybe this population or this whole lot of ball bearings was like 100,000. Out of those we selected 20 samples, and we decided to use this sample of size n is equal to 20 for estimating the value of mean and variance of the inner diameters of these ball bearings. So from these ball bearings we measure the inner diameters like this, and we find out that the average inner diameter of this sample was 1.495. Okay, it can be centimeters, okay, depending on the units of measurement we are choosing. And the variance of the variance that we observed in the inner diameters was 0.001, and these values are just for this sample of n is equal to 20. Okay, or the values which we have collected from these 20 items collected as sample from this whole large lot of ball bearings produced through a certain manufacturing process. Now these ones will act as estimators for the mean value of the inner diameters of all of this population and also the variance. Therefore we can write like this: the estimated value of mu, estimated value of the population mean or the mean inner diameter of all these ball bearings is equal to the sample mean. Okay, this one sample mean 1.495, and similarly the variance that exists in all in the inner diameters of all of these bearings is an estimation by the value of the sample variance we calculated from a sample set of n is equal to 20 ball bearings. It is equal to that one. Okay, now sample standard deviation is not an unbiased points estimator for population standard deviation. Okay, in fact they are related like this. So this is the value of sample standard deviation and this is population standard deviation. So they are linked with this factor here. Okay, and if you can recall from the previous slide where we saw that the sample mean was the unbiased point estimator for population mean and sample variance was unbiased point estimator for population variance. There we saw that E or estimated value of the value of sample mean was equal to the value of population mean, or we could say that the value of sample mean was equal to the estimated value of population mean, and the value of sample variance was actually equal to or considered as the estimated value of population variance, right? But this is not the case here. So these two values, the value of samples standard deviation and population standard deviation, are not equal. They are actually equated through this factor. Okay, and this factor is shortly represented as C4. So ES, or estimated value of population standard deviation sigma, is equal to C4 times sigma. Okay, and the value of this one can be found in the table which is given on the next slide. I will just show you after this. Or we can also write this expression as this one. So this one is the estimated value of sigma, which is equal to S, this one, or the sample standard deviation divided by this factor C4. Okay, so there is another method in which we can calculate, or in which we can estimate the value of population standard deviation, that is by the range method. So we can estimate population standard deviation by range method also. This one is suitable if we have smaller sample sizes, if you want to do it manually. So you know that range is actually the difference between the maximum value of the item in the, or the maximum measurement in sample, minus the smallest or the minimum measurement or the value in the sample. Or we can write it like this also: x underscore max minus x underscore minimum, the maximum value minus minimum value, or the largest value minus the smallest value in the sample. Okay, and here this R is representing range. So there is another term, relative range, that can be defined like this. Here the relative range is range divided by standard deviation of the population, and it is represented with W. Okay, W is another variable which is called as range, relative range. Okay, relative range is represented with W, and the mean value of W is represented with a constant D2. Okay, here it was C4 and here it is D2. So the mean value of this W is represented with D2, or we can say that the estimated value of D2 is equal to the value of W. Now from this we can write this expression, that the estimated value of sigma is equal to R over D2, and this one is calculated from the range. Okay, from the range method, and this method is useful for smaller values of n, and for larger values it loses its efficiency. Okay, efficiency means that it we need to work a lot if you're doing it manually. But if it is the value of n is less than or equal to n less than or equal to 6, then we can easily do it manually, and if the range increases, then it becomes a bit difficult. Okay, so the value of this d2 can also be determined, means that it can also be obtained from the table. Okay, so if you see, they look similar, both of them. However, here we are using standard deviation of the sample, and here we are using range of the sample. Okay, the value of C4 and D2 can be obtained from this table here. So this is the column for C4 and this is the column for D2 with the number of observations in one sample, and it is valid for 2 until 25. Okay, so when n is equal to or larger than 2 and less than or equal to 25, we can get the values of C4 and D2 from this table. Okay, that's all for this section.